Hi everybody, so yeah, thanks so much for coming, and Rudra, thanks so much for organising this. Really, you've done so much work for this, and yeah, we were discussing yesterday who should be the person to come up and introduce the workshop, and of course this should have always been you, because you've done a lot of work for this, so thanks so much for organising this. So yeah, for the first talk we've got Andrew Davison. There is some biography online, but I know Andy very well, so I can just give my own introduction. So Andy is Professor of Robot Vision at Imperial College London. I worked with him for many years. I have a lot of respect for his research. I'm sure many of you know the long history of work that he's had, and all the way back before kind of foundation models and world models became kind of the way they are today. And I think Andy's probably going to have a very different perspective on what a world model really is, all the way back to sort of, you know, geometric models and SLAM and all of that, and then interesting to see what your views are on today's sort of view of world models. So really looking forward to your talk. Thanks very much, Andy, and over to you.
Good. Okay. Hi everyone, and thanks for the introduction and invitation to speak here. Yeah. So as Ed explained, I've been working, I think, in this area of what I would consider world models for all my career, and maybe I just call it something a bit different. Spatial AI is the term that I have been using recently to mean, you know, long-term representation for robotics. So I'm going to explain a bit more about where that's come from and some of the things we're doing recently. So yeah, where are we headed in this area of robotics, or you might hear terms like embodied intelligence, recently embodied AI. You know, what are the long-term prospects? You know, I think we might try to build, you know, really quite general robot systems. So imagine, for instance, a robot that could tidy up a room. So you know, this is this really old video from Stanford of a robot apparently tidying up a room, but this is tele-operated. So clearly, you know, even this quite old clunky hardware from more than 10 years ago is capable of a lot, and what has been missing is something to do with the intelligence, the perception, the stuff that a human brain can obviously easily do. That's not to say that there isn't interesting work to do in robot hardware, because I'm sure there is. But you know, clearly what's mostly missing is something to do with the intelligence, or other products like this. So this is just a picture I found somewhere, but you know, big companies are now spending billions of dollars to try and build, you know, this sort of embodied intelligence that you'd actually wear and carry around with you all day. So this is a, you know, like prototype augmented reality system that would essentially enhance a human's intelligence by remembering everything that's going on, you know, recognizing all the objects and people. You can ask it where you left your keys, or you know, who's that person and when did I last meet them, or whatever it is. So you know, these systems, I think, require very much the same type of AI in order to work. And you know, in the context of this meeting of world model, so I think world model is, you know, a persistent representation of knowledge about the world that you're going to use to perform intelligently. Some of the questions that I ask about that is, how explicit does that model need to be? So you know, most of the work that I've been doing, as you'll see, has been building representations of scenes that are explicitly about 3D geometry and so on. Is that going to be part of the final kind of AI that we build that can enable these things, or will it be something much more kind of you know, implicit maybe? Yeah. So you know, we may ask the question: is a world model even needed? there are significant efforts going on now in robotics to say, we're just going to solve robotics via end-to-end learning. Do people really believe that's going to work or not? I mean, we'll hear from companies like Wayve later who are apparently doing that very, very successfully. Does that work just in some settings? Will that enable general AI? So you're not going to design an explicit representation. You're just going to hope that whatever representation is needed emerges via end-to-end training. And a final kind of question that I'm always thinking about is, what will be the interplay of learned and designed components in these sort of representations that we're building. So this is very much my kind of background. I've worked in visual SLAM, and SLAM, as I'm sure you probably all know, simultaneous localization and mapping, the essential problem of dropping a robot or other device into a space, and the device has to build a map of the space that it's in order to primarily solve the key thing of localization. Where am I? So you need to build a map so that you can localize. And SLAM technology is now in a lot of different sorts of products. Some of them that you probably know about, things like robot vacuum cleaners, I've worked on a lot. Drones, how does a Skydio or DJI drone hover in place or go out and come back? It's because of SLAM. But others you might not know so much about. So for instance, and this is linked to the glasses I showed you earlier, but something like a modern Oculus or Meta headset, or presumably the one from Apple works in the same way. How does it know its position in the scene so that it can deliver you these kind of rock solid graphics that move in the right way as your head move? They now work using visual SLAM, so they have cameras built into them, and they make a map of the world, and they use that to localize. Of course, they also use inertial sensors and other things, but cameras are really doing the heavy lifting. So that's the sort of technology that I have worked on. But these are very much kind of prototype products in terms of intelligent devices. They're nowhere near the kind of things that we saw on the first slide. So a big part of my belief is that we need to evolve SLAM into something bigger. So I never thought of SLAM as something that's just a fixed problem. I always thought the thing I was working on is representation for intelligence, and just we're trying to make that better and better. And one way of thinking that is adding levels of capability into SLAM and the representations that it builds. So that the systems that you saw in the previous slide, they're essentially making a model of the world which is a map of points, a set of sparse points in the world. That's the kind of minimum map that enables localization, but it's not a map of the scene that enables much other intelligent behavior. It doesn't allow you to know what objects are in the scene, or even to plan a path without avoiding collision, for instance. You need more detailed representation. The next kind of obvious level of representation is dense mapping. So this means not just sparse points, but really reconstructing all the details of the surfaces and shapes in the scene. And then levels above that, most obviously would include semantic understanding. So this means now knowing what objects are, knowing where they are, and knowing the things that you can do with them. But in my mind, this kind of SLAM way that we have of working, which is all about building prototype systems, make them run in real time, make them run with real sensors and real environments, actually demonstrate what they can do live, and gradually show more and more capability. I don't like sort of data set computer vision. I like to build into systems that we can actually demo, and that way of working I think is just still a really good way of working, and just trying to build more and more into that is the way that we're going to build up towards general spatial AI, I think. So this whole kind of area of what is spatial AI, what's it for, what does it require, I've thought about it a lot. If you're interested in more details about my thinking, I've got a couple of kind of white papers, really, discussion papers called Future Mapping 1 and 2, and you'll see the title of the first one is Future Mapping, the Computational Structure of Spatial AI Systems from 2018. And that sort of lays down my hypotheses mainly, that spatial AI is a fairly general sort of useful thing to do. It has fairly common properties, whatever the actual application is. And my belief is that building a representation of the scene which is somewhat close to metric 3D is useful. And I don't mean that like we should map the whole world at millimeter precision. At least the local area that you're in and you want to operate with objects and stuff, I feel like as a human, I look at this local area and I've got a really quite accurate 3D understanding that lets me do really quite, specific things with novel objects. And I think robots are going to need that. And that those sorts of really creative things that a human can do. I could pick up any two objects in this room and think of a new way to use one of them to interact with the other, for instance, things that have never been in a data set. And in my mind, that works by some sort of mental simulation. I look at the scene, I instantiate some sort of 3D model of what's there, and I can sort of mentally simulate what would happen if I did this and that. In my mind, that's the sort of system that we want to try and build. And there's plenty of questions there. How accurate should it be? How is it going to work? What representation should it use? I've thought about all of those things quite a lot. And again, this is a picture from that future mapping paper, thinking about how that high-level system would look at a sort of system level, and these kind of blocks of different computation, where the processing should happen. This part down here, that I call map store in that paper, is probably what you would call a world model. That's your persistent model of the world. But there's real-time data coming into that all the time. There's information going out that will go to actuators. Where should the processing happen? What are the right candidates for scene representations here? What's the trade-off between sort of bottom-up, always-on computation that will happen to your sensors as they come in, versus more sort of loopy top-down computation, which is guided by the tasks you want to do? Again, you can see evidence of all of this kind of thing in human vision. We're sensitive to all of the movements in a scene, independent of task. But on the other hand, when you want to do something specific, you direct your eyesight at the next thing you want to deal with. That's a very much sort of top-down sort of vision. What's the trade-offs of those kind of things? And particularly, and this is something I'll come back to at the end, what computation patterns enable us to do all of this with efficiency? Because if we actually want to build these embodied products, we need to pack all this into small, lightweight, low-power processors. We can't do all this processing in huge data centers on the cloud forever. Okay, so I'm going to show you a few sort of systems that we've built over the years, which show, I think, some kind of progress along these directions. So first of all, thinking about dense SLAM. So dense SLAM is meaning not just building a sparse map of points, but actually enabling really detailed real-time 3D reconstruction. So this was a system from a few years ago called Elastic Fusion, where we've got actually so this is a handheld RGBD camera that captures both images and depth, shown in the bottom left here. And here it is in real time, building a reconstruction of the scene. So this is representing the scene with millions of little circles, little oriented disks. Most of the processing here is done on a GPU for efficiency, and this system can do also things like closing loops. So you'll see that when the camera explores new areas, we see little bits of drift coming into the map. Any SLAM system will do that, but we can correct those and kind of loop it back in. So that's a kind of fairly classic and well-known system now. Interestingly, I think this system is really similar to something you might have heard a lot about in the last year or so called Gaussian splatting. So we've also worked on Gaussian splatting SLAM. So in fact, this is Gaussian splatting is a representation that's come out of graphics for how you can represent scenes with millions of tiny little blobs. Rather than just being disks, they're now sort of soft Gaussian blobs. But apart from that, it's really a very similar sort of point-wise representation. You splat enough of these things close together and it looks like a continuous surface. So we made a real-time Gaussian splatting SLAM system that won the best demo prize at CVPR this year. So it works something, a good bit of the video. So an interesting advantage of this over the Elastic Fusion is this now works really pretty well just with an RGB camera. So we're not using any direct depth measurement here. We've just got a color camera moving around. We're using that camera to hypothesize the positions of 3D Gaussian blobs and then optimize their positions to give us photo consistent views. So we're always saying wherever the new position of the camera is, first of all, keep rendering from our current scene representation and try and match the position of the camera to that. So we track the camera by doing that. We don't need to independently have an estimate of the motion of the camera. And then we're optimizing the position of the blobs such that when we render this scene, it looks like the images that we're capturing. And we also get nice properties like we can do pretty well at reconstructing, glass objects. We can see through them because these Gaussian blobs are soft. And I think, it's interesting to think about, where this method came from. It's in some ways a very classical sort of method. In another way, I think things that we've learned from deep learning about how just making everything smooth and differentiable enables us to optimize these very kind of over-parameterized representations in very simple ways. So this is all just kind of optimized with gradient descent. So one of the key things I'm always thinking about is, in building these representations for spatial AI, there's all these different choices about representations, but there's also all these choices about different sorts of learned versus designed components, and elements of neural network machinery come into these systems in different ways. So here's one that actually uses a pure neural network representation of a scene. So this came shortly after NeRF came out, and so NeRF was showing that a way of representing 3D scenes is to just use an MLP, a multi-layer perceptron, as a scene representation. The idea is that it's a neural network that you query with a 3D coordinate, and it will output some properties of what's going on at that coordinate, like the density of the scene and the amount of light coming in different directions. So we built a SLAM system based on that kind of idea of using a neural network directly as a scene representation. So again, this is a real-time demo of this system called IMAP. This is again working with a handheld RGBD camera that captures both color and depth. So one of the advantages of this over the previous system is this is actually quite lightweight in terms of the scene representation. So the neural network that's representing the scene here is actually really small. It only has about a megabyte of weights actually. So again, we're simultaneously optimizing for the position of the camera as it moves around, and then the neural network that's representing the shape of the scene. So in order to make something like NeRF work in real time, we had to do a few things. So one is that because we're using depth images, that just makes the whole thing easier. The other is that we do a lot of kind of sampling. So we're not just throwing all of the data into the optimization. We're sampling keyframes, and that's what you can see is this kind of red thing flashing around here. We're selecting frames, and then we're selecting which frames to use to actually train the neural network at each point. But then within the networks, within the keyframes, we're also sampling points. So these red dots you can see are the points we choose where we think we currently have most uncertainty about the shape of the scene, and therefore doing some sampling and training here would help. So this gives you a bit of an idea of the quality of scene that we can get. So this is done in about 5 minutes of scanning this camera around. We can build this kind of level of model of reconstruction of a room. And you may think, well, that doesn't look very accurate compared to, for instance, the things you just saw in Elastic Fusion. But it has actually some really interesting properties for robotics. So it's very sort of smooth and continuous. It's kind of, quite coherent. And it does things like fill in holes. So if there's an area of the scene you haven't seen very well on the floor, for instance, because the neural network just prefers to generate smooth, continuous things, it will just tend to fill that in. And there's another property we notice. So as this thing is training, and we're basically doing stochastic gradient descent on the weights that represent this scene, you can see it sort of wobbles around, but it wobbles in quite a coherent way. So for instance, this is a football on the floor, and you can see that its shape kind of wobbles, but it's not like random noise. It's like the whole football gets bigger or smaller, or its color might change a little bit. So that shows us that actually this football is represented really efficiently within the neural network. So I kind of interpret that as there aren't that many weights in the neural network that are involved in generating the shape of that football. So that really led us on to the next piece of work we did, which was adding a semantic layer to this system. So this is saying, we've got a neural network generating the geometry of the scene. What if we add an extra output head to that network and say, also try and generate the semantics of the scene? Because those semantics are very, very highly correlated to the shape of the scene, then we can supervise the semantics in an incredibly sparse way and semantically label the scene. So what you're seeing here is, as the camera's moving around the same room as before, with no kind of priors whatsoever, we're just going to add a few clicks here to say these points in the scene should have certain semantic labels, which I'm just defining, giving words here. And because the network wants to generate, coherent things, we only have to provide a very, very small number of these labels to label the whole scene really quite accurately. So we can label the whole room here with on the order of 100 clicks, because we're taking advantage of this coherence property. So that might be an interesting representation for robotics. But as I mentioned earlier, I think what's really useful and important for robotics is quite precise knowledge of objects in the scene. So is it better to represent the whole scene with some sort of semantic paint on top of it, or should we have a representation that goes more directly for what the objects are in the scene and where they are? So just a recent example of the quality we can do that with recently. So this is some work that shows what happens if we reconstruct a neural field. So actually this is the instant NGP method, producing a quite high quality neural field representation of a scene. So it's captured from a robot. So we move a camera like this. So there's a camera on the wrist of the robot. We capture a set of color images. We train a NeRF-like neural field representation, which gives us a density map of the scene like this. And then we can fit 3D object models. So these are just some CAD models of objects that we have known in advance, and we can fit them to this scene. But we can really do that incredibly accurately, so down to kind of millimeter precision here. So even for the sort of tricky objects like screws and bolts here. So what can you do if you have this object-like representation of a scene? So you can do really sort of sophisticated manipulation. So think back to the goal of doing something like So going back to some of these really tricky goals in robotics, like tidying up a kitchen. Here's a sort of demonstration of a little setup a bit like that, where we've got a messy pile of objects on the table, and we want to put them away in quite precise places. So a lot of the robot grasping demos you'll see will just be picking up objects and kind of dropping them somewhere. But here we want to pick up objects and really place them quite precisely. So this kind of view here is showing, you can think of this as like our digital twin of the world. So because we've actually accurately estimated the positions and identities of all of these objects, because we have strong models of them, we can know exactly what those objects are, exactly where they should be placed, and even tricky things like, this object, we can't directly grasp it in the correct way to be able to place it where we want to. We need to drop it so that it can reorient, and then we can place it precisely. So I would argue that powerful kind of 3D scene understanding enables that, and it would be really hard to do this kind of thing without that, unless you just learned and seen so many different things that maybe you've seen everything. So a limitation of that method, and sorry I'm jumping around a bit fast there, but a limitation of that method is you do need these precise knowledge of the exact objects that you're going to use. Clearly that's not very scalable necessarily, but modern vision tools are actually coming in that enable us to build these more sort of token object-like representations of quite general scenes now. So for instance, some really nice recent work from Wayve, who's here, who was working with Roberto, of course, for many years on this work of training neural networks to accurately predict normals from images. So a normal is just the direction, the orientation of a surface at any particular pixel. So these are just incredible results of a neural network that can look at an image, and because it's seen plenty of images with ground truth normals, it can have a pretty good estimate of the shape of the normal at every pixel. So other front ends that have come in now from deep learning and again proven to be really good are for instance segmentation. Again, a problem that just seemed staggeringly hard to me for many years, now works pretty well. So if we combine this normal prediction with, so this is the segment anything network from Meta, we're going to build a SLAM system that works at the level of tokens. So the way this works is that each input image, we feed it into the normal network and the segmentation network. And what comes out of that is regions of the image for which we've got a pretty good idea of the boundary. So we don't know what this object is, but we've got its shape in this 2D image. And then we've got the normal field. And actually we can locally integrate up the normal field to get an estimate of the 3D shape of this object. But there's still something important which is unknown, which is this a sort of small object which is close to the camera, or is it a big object which is far away? So we don't know that kind of more global parameter. And of course there are neural networks that can predict the depth of things, but actually they don't work that well. They have, compared to predicting normals, it's a much harder thing to do, and often you'll just make errors with things like that. But because we've turned our image into these chunks, we can then solve that in a sort of multi-view way. So here are all the different hypotheses of the depth and size of this object. We project those into a nearby image. So this is just another frame that the camera has taken a little bit of time in the future. And then we optimize. So for all of these object chunks, we slide them around in 3D until they're photo-consistent across multiple views. And this actually works incredibly well. So we're not changing the local shapes of the objects. We're just assuming that this front-end segmentation and normal prediction is good enough that these local object chunks are pretty accurate, and we're just moving the chunks around in 3D. So I think of this as a fairly general form of this sort of object level SLAM. Of course we could also get names and identities for these objects quite easily out of neural networks. But this is a very sort of powerful way of building potentially a very efficient SLAM system, I think. Okay, I think I'd better move on and just come back to kind of my main theme. So, how are we going to build this spatial AI system? So, we want to do all of this and make it efficient. What will this map store look like? And I don't have the answer to this. Will it be something like a Gaussian splatting set map of blobs? Will it be something more explicit like a graph of the objects in the scene? Will it be something much more implicit still, like some weights of a neural network that are quite hard to understand, but at least there's an area of memory that we say this is the world model, this is the map store? I'm not sure. There's many options there. Probably my guess is towards this sort of object graph. That is a useful long-term representation of a scene. But if we want to make all this work efficiently, so working on choosing those representations is important, but there's another issue that I think we should work on, and where we can make a lot of progress, is to think of how this whole kind of system maps to the hardware that we're going to run it on. So I think we're at a very interesting point in AI and computing research in general, where we've been working for so many years with computer processors and sensors that have been designed for other things. So obviously general purpose CPUs, they're good for everything. They can run word processors. GPUs, of course, everyone knows about those now, but they were really designed to do graphics. They're massively parallel. They're actually really good at running certain types of neural networks, as we know, but I think they're far from the ideal hardware we want for AI. So in fact, we had a rather long project on this. This was back 2013 to 2018 with partners at Imperial, Manchester and Edinburgh, so including this was Steve Ferber's group at Manchester. So thinking about this relationship between algorithms and the processors that they run on, and thinking about SLAM algorithms, running on, from a big desktop machine right down to, tiny embedded boards. Where are the opportunities for accelerating things? Where are the bits where parallelism can really be taken advantage of? And to be honest, the goal of this originally was, can we design a chip for SLAM? And we didn't really manage that, mostly because I think the algorithm space was shifting too much in my mind, and others, I had so many different ideas about how we should do SLAM that, taking that 5 to 10 year decision to say I'm going to bake that algorithm into hardware just seemed premature to me. But then I heard about other things that were going on. So, when you're designing new hardware, you have to make a bet about what's going to be important. You could bet on really specific algorithms and make a processor that really just accelerates one particular algorithm, or you could make more general choices. So I heard about things like GraphCore, and this is a slide from them, the company based in Bristol. So they have this IPU chip that's a massively parallel chip. So it's massive, it has many processing tiles on one chip, so similar to a GPU in that regard, but it's a much more general type of parallelism. So all those different tiles, you can think of each one as like a little separate CPU, really. It can run its own program in its own time, and it has its own local memory. And the really important part about an IPU is it has tons of high performance local memory around each of those processors. They're actually on the chip. And then it has this kind of all-to-all interconnect structure that means you can pass messages around between those chips. So the sort of algorithm that has the right flavor to work well on that is you divide up your processing and your storage, and you operate locally on memory wherever you can, and then you pass messages around to keep everything kind of synchronized. So rather than thinking of next job to do, bring in all my data, pass it through my processor and pass it out again. The problem with that, and that's the sort of GPU style, it is you have to move loads of data around. This is saying keep your data in the same place if you can, operate on it locally. So a lot of what I've been thinking about in the last few years is how do we take that kind of computation to SLAM. So particularly in the Future Mapping 2 paper, I'm really focused on algorithms that have that character, and in particular Gaussian belief propagation is this algorithm for solving the sort of optimization problems we have to solve in SLAM, which are probabilistic, optimizations on factor graphs generally, but solving them with a local belief propagation message passing style, where you can keep everything local and you just pass messages around these big graphs, and you can actually solve problems like bundle adjustment by doing that. So this for instance was some of the first work we did where we actually implemented this on GraphCore's processor. So you take the factor graph for bundle adjustment, which is like the classical optimization problem that you have in 3D vision. So you have the factor graph that represents variables for cameras, variables for points, factors for measurements, and you just directly map it down onto the tiles of the graph processor, and then you solve it by passing messages around that graph. And this can take full advantage of the parallelism of perhaps these chips that may become mainstream in the future. Okay, so I think I'd better conclude. So yeah, I think that spatial AI research is really important. So yeah, we'll hear a lot about world models. I think it was mentioned in the introduction that a world model is not just about representing the shape and structure of a scene. Of course, I understand that. It's also about understanding the things you can do, the actions you can take, maybe the actions that other agents in that scene may take. But for me, I just still think getting from real sensor measurements to representation is probably still the hardest bit. I think if you had a perfectly high quality 3D simulated, think of like a game physics model of this room, and then you had just standard kind of motion planning or something, or some quite simple learning, a robot could do an incredible number of things in this room. But the hardest bit, I think, is getting to that representation, from real sensor measurements, and doing that efficiently, and doing it with all of the constraints of real hardware. So that's what I call spatial AI, and that's what I think is really important. So yeah, representations for spatial AI will have significant learned components, but tied together, I think, by structures or algorithms that are so specific and so sort of, yes, so specific. So things like geometry manipulation, rendering, physics, Bayesian fusion, these are pretty fundamental things. Are we really going to learn all of those, or should we might as well just design them in? Because I think, if we learn them in the end, we might just end up with these things anyway. And also just building systems that a human can look at and have some understanding of how it works. I think there's also a massive advantage for that. So we may as well design some of these things, is my point of view. And then I think really important research, and possibly the most important research, is how do we make this all work efficiently, and the computational patterns of the representations and algorithms, and how they're represented to the processing and sensing hardware that are coming, that will be really specifically designed for AI. These may be the most important research issues in the next few years. Okay, I better finish there. Thanks a lot.
Thanks so much, Andy. So let's take some questions. I think hopefully we can push back into the coffee break by 5 minutes or so. So yeah, any questions from anybody? Yes.
So, and thanks for the talk. I have one question, like how, in your opinion, how do differentiable simulators, like with differentiable physics and differentiable rendering, comes apart with spatial AI?
So differentiable simulators. So, I mean, clearly you can use those to train, many of the components that I think are important here. So, for instance, the normal prediction network that I shown was largely trained on synthetic data, and I think if you were moving to more the not just understanding the world as a static graph of things, but you wanted to understand the way that those things move and the physics of them, then I think differentiable simulators would also be an important part of that. I do think that a lot of the training data that you need for the learned components of these systems can come from those sorts of simulators. But and another point would be to say, some people, you talk about sim to real or whatever, and you've got a simulator, and you're going to train something on that and then use it in runtime. I would always ask the question, well, why not just make that simulator part of the runtime system? If spatial AI can instantiate your simulation with the state of the world, and then at runtime you just run the simulator and do like model predictive control, and that the only reason not to do that would seem to be if it's too expensive, and perhaps training a neural network can very quickly get you to a quick answer, but probably you'll still need to come back to that iterative sort of solving to do something really accurate.
Yeah, so in most of your talk, you worked around dense representation of the world.
Mm-hmm.
Do you think this is the way to go towards spatial AI? There was a time that we were thinking about sparse representation of the world. Was it just for computation, or?
So it was definitely for computation to start with, but I think there are these recent representations that are more like object graphs, so like the sort of super primitives one. It's dense in the sense that it's trying to represent everything in the world, but it's sparse in the sense that the sort of optimizable state is actually something quite small again, because you assume kind of local coherence of those chunks. So I think that that's probably the best of both worlds actually.
Yes.
Thank you for your talk. You mentioned a lot of different applications at the beginning. Do you think there are generic representations that could work for any task, or do you think that we should focus on more task-specific representations?
I mean, that's a great question. Clearly there's a high role for task-specific representations, but I think the most general intelligence, and that sort of creative intelligence, the things that humans can do, like looking at novel objects and thinking of what you can do with them, I think that motivates a quite general task agnostic representation actually. So I still feel like as a human I can glance at a table with a lot of junk on it, and I've got this sort of quite general 3D physics type picture of that scene in my mind, independent of what I'm going to do with it, that allows me to think of new things. So you may say think about a robot playing tennis. There's that step of how do you first hit a tennis ball, and even thinking of what to do. Is it more impressive to do that, or is it more impressive to go from that to playing like Roger Federer? That seems like a very task specific. Then you'll just train. neural network type thing. Whatever goes on in Roger Federer's head, he's not actively simulating every shot. He's doing this or modifications or an interpolation of all the things he's done a million times before. But I think it's more interesting to get a robot that could do those sort of things for the first time. And I don't think it's a big data thing. I think it's representation and then relatively small amount. So yeah, a lot of people are saying robotics is a big data thing. I have serious doubts about that at the moment. But I bet you'll hear a lot of opinions to the contrary today.
Okay, great. I think we'll have to end there because I want to give time for the posters in the coffee break. But thanks so much, and I think it's something I've learned a lot from working with you is, if you really think about computer vision properly, you get much more data efficiency than just not thinking about it properly. So I learned a lot from that as well. So thank you very much, Andy.